Okay, so now let's have an example. We're going to roll 2 dice, and we're going to let the discrete random variable y be defined as the sum of the dice. So what's the expected value? Well, we remember we're going to go something like this. Probability of y. Oops. There we go. It's kind of acting a little cantankerous. And we're going to sum it all up, right, like that, right? So, you know, if y is 1, what's the probability of 1? That's going to be 1/6, something along those lines if we were just doing 1. But let's go on. Okay, now, we remember, though, we've got 2 dice. So, actually, the probability of us rolling a 2 is going to be 1 out of 36, right? Because that's that elemental event. And likewise 12, and for 3 it's going to be 2/36, right? And then 11, you know, is going to be the same probability. And so you can expect then that if we wanted to compute all of the expected values, we could do that, go like that, and I'm not actually going to do the whole thing, but I'm going to start it out for you. So we're going to say it's going to be 1 out of 36 times 2 plus 1 out of 36 times 12 plus 2 out of 36 times 3 plus 2 out of 36 times 11. Oops, 11. And so you get the whole idea. You're just going to take all of those probabilities times the value of each particular event occurring, and you sum that all up. And what do you get? 7. That is the expected value that you're actually going to get in this particular case. Remember that in this case, all the outcomes were not equally likely to occur, and so we had to be careful in how we were summing everything up. Later, we'll see that we'll need to develop more complex methods than just simply counting to construct probability functions. So, economic application of expected value. Consider a lottery game where a 3-digit number is selected at random each day. If you match the 3-digit number, order matters, you win 500. So if we purchased 1 ticket each day, will this be a good investment? Each ticket costs $1. So let a discrete random variable W be, that's actually the amount we win per day, right? So we're saying in this particular case, it's 500 if we win and 0 if we lose. Well, we could define this a little bit differently. We could say it's -1 if we lose, and then you'll see how that would play out if we did that. But we won't do that this time. We'll simply say, let's see, that the probability, this probability of that W is going to be, well, 1 out of 1,000 that we're going to win $500. But it's going to be 999 out of 1,000 that we're going to win 0. Or we could say -1 if we wanted to, but we won't. And it's 0 elsewhere. So we can then compute our expected value. And that will be, let's see, well, we're going to take our W, we're going to let it run from -infinity to infinity of W, P of W. So let's see, we're first going to say, okay, we could win nothing, a group at nothing, and we have 999 out of 1,000 chances of doing that. And then we're going to add in the other, which is we can win 500 big bucks, and we actually have a 1 out of 1,000 probability of doing that. And so that means that we've got an expected value of winning 50 cents a day. So we'll say, hence, we will win about 0.50 per day on average. Yay! But the problem is, costs us $1, costs $1 a day to play. So we're just kind of SOL. This is not really a very effective way to make money, even though it might be a little bit fun in accordance with our neurological underpinnings. Okay, properties of expected value. The expected value is a linear function, so if we offset it a little bit, well, we can treat it exactly as we always treat linear functions for any constants a and b. So, of course, that was very simple, so I have to make it look like it's more complicated by giving you an example, but you'll see that this is actually simply just as simple as the previous equation. So we'll suppose the cost of raw materials for a single shift of production is $1,000. This is the B. And plus $25,000 times, so that's like the A right there, times the number of the finished parts produced. So this is like A. So the average number of expected parts produced in a shift is 257.9. What's the average cost of raw materials for a single shift? Well, let's see. We just figured out the expected value right here, right? Well, we didn't figure it out because they gave it to us. So we can say the expected value of the cost is going to be, well, the expected value, 2,500 times the number of parts plus 1,000. And that's 2,500 times the number of parts plus 1,000. And, well, what's that? 25,000 times 257.9 plus 1,000. And that gives us 4,575.0. There we go. Notice this is one of those problems that if you just saw this cold and hadn't ever seen it before, it would seem very confusing as far as how to do it. But once you see how to do it, it's just as easy as 1, 2, 3, or 645,750. Okay, so what are the properties of expected values? Well, the expected value, well, we've talked a little about the properties, and now you're going to see that the properties continue to be more or less the same. The expected value of any function is going to be, well, we can calculate it pretty much the same way we would expect to calculate. If we want to figure out the expected value of a function, what do you think we would do? Well, we're probably going to take that function at a particular x. We're going to figure out the probability of that function at x, multiply them together, and do that for the whole gamut of possible values, and add them all together. That's pretty much just what, before we had an x there instead of a g of x, but it's the same essential idea. In fact, in general, we can say the expected value of some function is not going to be the same as a function of the expected value. Oh, that's you'll see that just makes sense. So you can say the expected value of x squared is not the same as the expected value itself squared, right? And this particular thing is given to you right here because we are going to see in the future that these two, we're often taking the difference between these two values, and so they better not be the same all the time, because otherwise we would be hopeless. in the face of uncertainty. So this property and the previous one holds for either a discrete random variable or a continuous one. Now, the variance of a random variable x is defined by, we're going to put our little variance of x. Well, what do we want to do? We would like to find the expected value of, well, let's see, wherever our function actually falls, that x, and its distance from the average of that function. So this gives us sort of a little bit of a gauge of how much any particular value is different from the average value. We'll take that, we'll square it to make it so it's always positive, right? Go like that. And that's our variance right there. And we notice that the variance has always got to be equal to 0, and we did that cleverly, and that's why we squared it. We squared it, so that gives us this term that's like not in the same sort of units as x itself. So to get it back in the same sort of units as x itself, we use the standard deviation, which is simply defined as the square root of the variance. And the units of this standard deviation are the same as those of the random variable. Now, an alternative method for computing variance, and this is a little bit of hocus pocus here. Normally I don't like to do derivations because we're engineers and we don't need to derive things. It's kind of like proving theorems, but in this case, this little bit of hocus pocus actually will come in handy in the future if you understand how we get it. So we're going to unpack, as they say, this particular, oops. And there we go. Okay, so now we've got all of my parentheses and brackets in good shape. So if we're trying to figure out this particular value, the expected value, the way to do it, now we can look at this. I'm saying that it's x minus expected value and all of that stuff squared. So let's do that. Let's take this stuff out here, unpack it. So this is squared, so it's going to be x squared minus 2 times x times e to the x, or expected value of x, plus expected value of x squared, or squared, expected value squared of x. Okay, and so we'll put that all in our expected value, and then we will say that, okay, now watch this part, this little sleight of hand. There's a little tricky part here. We know we can do each of these parts separately because this is linear. Well, we can take each one of these added quantities, let's say. So expected value of x squared is going to be expected of x squared. Whoops. Okay, so now we can go to the second added item. So that's going to be minus, if we say minus, okay, I'll do this really painfully right here. So, okay, what is the expected value of 2? Well, okay, I'll write expected value 2. What is the expected value of x? Well, expected value of x. What's the expected value of the expected value? Well, let's see. Wouldn't that be the expected value, right? If the expected value of the expected value is just the expected value. And then I'm going to do this the second time, right? Or I'm going to do this last part right here. What's the expected value of the expected value squared of x? Okay, so now we've got it all rewritten here. Now we can call this, we'll call this expected value of x squared minus, well, what's the expected value of 2? Watch this, it's a trick. Expected value of 2 is 2, right? It's constant. expected value of x times expected, okay, that's ex squared plus, and then expected value of the expected value squared. Oh, okay, well, it's just expected value squared. Now, look, we have the minus right here. Oops. Minus 2 plus 1. This all becomes expected value of x squared minus expected value of x, and then square that quantity. That's the difference I was talking about there. That better darn well be different sometimes, because otherwise our variance will never vary and we'll be in trouble. So this is an easy way of calculating the variance on occasion. This is the key equation right here, and you'll need this on solving some homework problems and test problems and so forth. So a discrete random variable, the variance for a discrete random variable becomes something like this. And remember, this is x minus the mean, that's the expected value right here, times the probability of x. And this, again, is just what we had worked out. So all of this is what we just worked out, but written in a slightly different form. So these are very neat formulas. I know you love them, but what are they actually telling us? Here's what they're telling us. If we look at random variables x and y, and they both have the same mean, okay, so they're both mean with 0. And we can see that, right? If we wanted to, we can say, well, let's see. If we took x, each individual value, multiply it by its probability, we'll do it for this one. This one would be, first, the value would be minus 1, and the probability is going to be 0.3 times 0.3. And then it's going to be the value of 0 with a probability of 0.5. No, 0.4, sorry. And then we're going to have a plus 1, which is going to have a probability of 0.3. So we add those together, and after all of that work, we determine that the expected value is 0. And you'll just have to trust me, if you do the same sort of thing with this, you will find also the expected value is 0. But guess what? These are really quite different. Look at that. So the means are the same, but the variances are quite different. So we can see that. If we calculate the variance for this one, and remember, how are we going to calculate the variance? We can simply say that, well, now let's remember how we calculate variance using our simple formula. It's going to be ex squared minus e squared x. Okay. So what is the expected value? Expected value is just the mean. It's just 0, because that's the mean. And we calculated it. We calculated in boring detail. Okay. No, that doesn't say bovine detail. It's boring detail. Okay, so this part, how did we calculate that? Well, we would just calculate it by saying it's going to be, remember, instead of saying probability of x, that's how we calculate expected value, right? That was e of x. So e of x squared has got to be summation of x squared times probability of x. So in this case, it's going to be minus 1 squared times 1/3, or, well, no, 0.3. I'll be times 0.3 plus 0 squared times 0.4 plus 1 squared times 0.3 again. So this is actually equal to 0.6. Got it. Okay, so that's the expected value in this particular case. But if we do that same equation over here, and trust me, it turns out much larger. It's going to be what? Minus 4 squared. I'm not going to do it all the way, but minus 4 squared times 0.05 plus minus 3 squared times 0.05, and et cetera, and et cetera. And you might say, okay, we can add all those things up, but remember we've got to subtract off minus the expected value squared of x, but that's just 0, so we don't really need to subtract it off, even though we are subtracting it off. But you can clearly see in this case that the variances vary between these two. Okay, so in conclusion then, we can say that variance is a measure of the outcome, of the amount that the outcome can vary from trial to trial. The larger the variance, the greater the chance the outcome will be further from the mean. That's okay. What if the variance is 0? Well, that just means the process will always be the same. So actually, it means we no longer have a random process. It's deterministic, and it's much more boring. So for any constants a and b, we can say the variance, this is a little bit different than the mean. The variance of x plus b is just going to be the variance of x. And the variance of some value multiplied by x actually turns out to be a squared times the variance of x. Now, we want to lastly come up with the definition of the cumulative distribution function. And cumulative distribution functions are really pretty simple. They're just the probability that you're going to get a number that's less than or equal to some predefined number. So this is the equivalent of me saying, what's the probability that I'm going to roll a 3 or less if I roll one die? So that definition applies for either discrete or continuous random variables. If x is a discrete random variable, then we can say that f of x is simply equal to probability of some I running through, minus I, or minus infinity. So in essence, it simply means that we add up the probabilities of it, the value or anything less than that value occurring, and we just add those probabilities together. So once you see what we do next, when we give an example with the die, I think it will become crystal clear. So we're supposed to roll a single die and let the random variable be defined as the value of the die. And then we're supposed to determine the cumulative distribution function and plot it. So if we do that, we can say that, first off, the probability of rolling a 1 is going to be, well, what would you expect it to be? It's going to be 1/6, right? Probability of rolling a 2 or less is going to be, well, we can roll a 1 plus a 2, so it's going to be 2/6. And then what's the probability we could roll a 3 or less, and so forth. You say, what's the probability I could roll a 7 or less? Well, it's going to be 100% because we can't even roll higher than a 6. So cumulative probability functions are really pretty darn straightforward. Now, the properties for cumulative probability function, of course, they're going to range between 0 and 1. And cumulative distribution function is a monotonically increasing function. So that means that if you've got an x of I, which is a little less than x of j, then simply the cumulative distribution function is going to vary in exactly the same way. So the one cumulative distribution function evaluated at x of I is going to be less than evaluated at x of j. And moreover, the limit as the cumulative distribution function, as that x goes towards minus infinity, has got to be 0, and in the other end, it's got to end up at being 1. So finally, for any values, a is less than x is less than or equal to b, well, you can imagine, all you need to do is take the cumulative distribution function evaluated at b, subtract off that value of a, and it's very much like the idea of doing a simple integral. Let's see, if this is b, this is a, we can subtract off the value of the cumulative distribution function for everything less than a and anything greater than b, and then that will give us this area right here. So this is valid for a discrete random variable or a continuous random variable, and you've done great. You can relax now.